Hello students, in this video we'll find the eigenvalues of the adjugate matrix. Let's be given an n by n matrix A, and recall that the adjugate matrix is the matrix of cofactors Cij of A transpose, where Cij is the determinant of the matrix of A with row I and column J removed, times -1 to the power I plus J. Okay? And of course, from previous videos, we have the following relationship, right? So for A invertible, so if A is an invertible matrix, then the adjugate of A is going to be equal to A inverse over the determinant, right? So A times adjugate of A, then we have that A times this thing is just going to be the determinant of A times the identity matrix, right? And therefore, what we can say is we can say that the adjugate of A is really the inverse, is really A inverse times this determinant over here, right? So in other words, if A is invertible, this says that the adjugate of A is A inverse times the determinant of A, like that. Excellent. Okay? And so now let's figure out how this adjugate works under similarity, right? So under similarity, what happens? So suppose, here's a little proposition. So prop, if A is equal to P inverse B P, then let's find the adjugate of A, right? So let's assume that A and B are invertible in this case, right? So A, B invertible, A and B invertible. Then what can we say? Then we can say that the adjugate of A is going to be the determinant of this thing over here, is going to be the determinant of A, which is going to be P inverse B P, right? Times the inverse of P inverse PB, which is going to be what? Which is going to be P inverse B inverse, and then what? And then a P, right? Now, of course, this is just going to be the determinant of B, right? And the determinant of B is equal to the determinant of A, so I can write this as just the determinant of B, determinant of A, determinant of A, and then I have the inverse over here. So then what we can do is we can write this as P inverse B inverse P, like that. Okay? And so now what's the relationship between this thing over here? So now, of course, this determinant of A is determinant of B, so I can write this exactly as, this is going to be equal to P inverse, and then determinant of B if I want, because determinant of A and determinant of B are the same by this formula. And then what? And then we're going to have a B inverse, and then P, right? And so in other words, that's just the adjugate of B, right? So this is just going to be P inverse adjugate of B times P, right? So in other words, if we have this relationship over here, then the adjugate of A is P inverse adjugate of B times P, like that, right? So that's the rule for adjugates under similarity, right? Excellent. And so now, of course, I want to find the eigenvalues of the adjugate, right? And so here's what we're going to do, right? So let's do the following. So let A, by Schur's lemma, A is equal to U T U transpose, which is U T U inverse, where here T is upper triangular, and U is unitary, meaning that U inverse is equal to U transpose or conjugate transpose, since I'm assuming these matrices are real over here, right? So Schur's lemma over here works in generality over here. So now I can say, as I can say by continuity, I can pass the adjoint formula over here. So the adjugate of A is going to be U, the adjugate of T, and then U transpose or U inverse over here, right? And so now the eigenvalues of the adjugate of A are the same as the eigenvalues of the adjugate of T, right? So in other words, this implies that the spectrum of the adjugate, by unitary similarity, the spectrum of the adjugate of A is equal to the spectrum of the adjugate of this upper triangular matrix over here, right? And we also know that since T is upper triangular, the diagonal entries of the upper triangular matrix are exactly the spectrum of A, right? So we also know that sigma of A is equal to sigma of T, right? In other words, the eigenvalues of A are the diagonal entries of this upper triangular matrix, and that, of course, is just T11 through Tnn, the diagonal entries of that matrix over there, right? And so now that's great, because what we can do now is we can say, okay, well, I can figure out what the spectrum of the adjugate of T is, right? So in other words, if we look at this upper triangular matrix T, so what does T look like? So T looks like this. It looks like T11, T22, all the way down to Tnn, and there's some elements above it and some elements below it over here, right? So for example, if I was to look at the, what will the adjugate of this thing be? I'm going to transpose, right? And what will the key features if I look at the minors of this thing over here, let's look at the 1, 1 minor, for example. So what would the 1, 1 minor of T look like? Will be -1 to the what? -1 to the 1 plus 1, which is going to be a positive 1. And that's going to be, I'm going to punch out the row and column which T1 resides, and that's still going to be upper triangular, right? So that's just going to be T22 all the way down to Tnn, which of course I'm going to write that as lambda 2 times lambda n. If we look at the C22 of T, what would that be? Well, I punch out the 2, 2, and I just have the diagonal entries of what's left over, right? And so we T11, T33, Tnn, which is going to be a lambda 1, then a lambda 3, then a lambda n, et cetera, et cetera, et cetera. If I go down to Cnn of T, right, what would that be? That would be just T11 all the way down to Tn minus 1, n minus 1, which is lambda 1 through lambda n minus 1. Beautiful. Okay? And so, of course, now, if I do the adjugate, I'm going to transpose these things, so all the other minors over here that aren't 0 are going to flip over there, and so we see that the adjugate of this upper triangular matrix is also going to be an upper triangular matrix over here. And so what we're going to see is that these are the diagonal entries of the adjugate matrix over here. And so those are the eigenvalues of the adjugate of T, which are the adjugate of A. So that tells us now that the adjugate of T is just going to be what? All things of this form. So this is going to be all possible values lambda, such that lambda is equal to the product j goes from 1 up to n of lambda j, but j is not equal to I, for I equals 1 to all the way up to n. So in other words, we're just punching out one eigenvalue every time over here. So in other words, we have these values. So in other words, if, for example, you had n is equal to 4, right, then what would the spectrum look like? The spectrum would look like this. It would look like lambda 2, lambda 3, lambda 4, lambda 1, lambda 3, lambda 4, lambda 1, lambda 2, lambda 4, and lambda 1, lambda 2, and then lambda 3. That would be the spectrum of the adjugate over here. So in other words, the spectrum of the adjugate of a matrix is it's the product of the eigenvalues of the original matrix, so one of the eigenvalues punched out from that product. So in particular, what that tells you is that if the matrix A has an eigenvalue of 0 with a multiplicity of 2 or more, then all the eigenvalues of the adjugate are 0. So that's a very cool application of this formula over here. So if we think about the eigenvalues of the adjugate, we want to think of the product of the eigenvalues of the original matrix with one of the eigenvalues punched out, and that gives us a spectrum of the adjugate. Thank you very much.